Welcome to this video from Derby Physics Tuition, and I've been working with a student studying gravitational fields and namely gravitational potential, and this video will look at what gravitational potential is and why it has a negative value, and this area in the study of fields students do find particularly challenging, so hopefully this video will help you with your understanding of gravitational potential. So let's have a look at the situation. Now we've got a mass m which is resting on the surface of our planet Earth, and we decide that we want to raise that object to a height h. Now from GCSE it will have gained gravitational potential energy, and the formula for gravitational potential energy is given by mgh. So we've raised it through a height h, and that is the amount of gravitational potential energy it has. Now the problem with this formula, it worked okay at GCSE, but if you move the object through greater heights h, the gravitational field strength doesn't stay constant. So the further you move from the surface of the planet, g reduces, and so that creates a problem when we're talking about objects which are at large distances away, for example other planets or moons or satellites. And we're interested in this area because we put satellites into space, and because space travel is so important. So how can we develop an equation without little g in it? So let's have a look at how we do that. Now the other bit of physics from GCSE was that we to lift that object we have to do work, and in physics the work done is given by the force times the distance moved in the direction of the force. Now the force is lifted through a distance h, so our work done is force times the distance h. Now in your earlier study of fields you would have come across this equation for gravitational field strength, which is g over r squared. So capital G is a gravitational constant, capital M is the mass of the planet, and r is the distance from the center of the planet. Now if we use our work done equation, so our work done, okay, is the force times the distance, so it's the weight of the object that we're lifting, okay, and we're going to use the distance from the center of the planet. So we're going to use the distance r. So the object is at a distance r from the center of the planet. So what I'm going to do is put in my value of g into this equation. So we get g over r squared times r. Okay, and this r will cancel with one of the r squared terms at the bottom, and so you're left with that the work done is gm over r. So the work done, or the change in gravitational potential energy, we've now got a new formula for it, and it doesn't involve little g, which, as we discussed at the beginning, changes the further you move from the surface of the planet. Now that's all well and good. We've got a nice equation, and it's related to the mass m that we are actually lifting from the surface of the planet, this term little m. Now, but that is so this equation is specific to that little mass m. So we'd like to have a more general equation. So if we take the equation that we had, that we just derived in the previous part of the video. Now what I'm going to do is divide both sides by little m. So we've got the change in gravitational potential energy divided by the mass, and we're left with gm over r. Okay, now this term here is known as the gravitational potential, and it's got a symbol V. Okay, it's a little bit confusing because we use that symbol for potential difference or voltage as well, so it's not the greatest symbol to choose, but gravitational potential can now be written as that equation. So when we divide the gravitational potential energy by the mass of the object, we end up with this term here, and this is what is known as the gravitational potential. So it's the gravitational potential energy per unit mass. Now it actually has a negative value, and in the next part of the video we're going to look at why gravitational potential has a negative value. So why does gravitational potential have a negative value? Well, we're going to revisit from some GCSE physics first. Now imagine that I've got an object here with a certain amount of gravitational potential energy, and I decide to release that object. As soon as I release it, it will fall straight away, and there will be that gravitational potential energy will be converted to kinetic energy. Okay, and it will reach a maximum value just as it hits the surface of the Earth. So what I want you to take away from this bit is that when we release our object, it gains kinetic energy. Now let's have a look at a situation where we move to a certain distance away from Earth. Now the way the gravitational field strength falls as you move from the surface of the Earth is shown by this graph here, and it's actually an inverse square relationship, and we're going to, so it basically falls away like that. Now at the point where the gravitational field strength reaches 0 will be at infinity, so you would actually need to move at infinity for the gravitational field strength of the Earth to actually be 0. So we're going to move our object and place it here. Okay, and that distance is actually infinity, and the mathematical symbol for infinity is that. Okay, now if we move our object to infinity, its gravitational potential energy will be 0, and if I release that object, it will fall and it will move towards the Earth, and it will gain kinetic energy. Now how can that be so? How can we start with an energy value of 0, gravitational potential energy value of 0, and we're suddenly gaining kinetic energy because we've released our object and we're letting it fall back towards the surface of the Earth? It's gaining more and more kinetic energy. Now we talked about the fact earlier in the video that when you drop an object above the surface of the Earth, the kinetic energy increases, and the gravitational potential energy decreases. So the gravitational potential energy at this point must be lower compared to what it was at infinity. So how can we mathematically deal with that? That the fact that we've got a value of gravitational potential energy as being 0 at infinity and lower as this object gets near the surface of the Earth. And the only way that you can deal with that is that we have to say that the gravitational potential energy is becoming more and more negative. And so that's why in our gravitational potential formula, which we derived earlier in the video, we have to give it the value of gravitational potential a negative value. And you can see from this simulation here, the fact that the gravitational potential starts at 0 and is decreasing must mean that the gravitational potential takes on a negative value, and it becomes more and more negative the closer you get to the surface of the Earth. So I'm going to finish off this video by looking at the definition of gravitational potential and why it has infinity in the definition that you have to learn, and hopefully by appreciating our treatment of the object when it starts at infinity, you can see why infinity is included in the definition. So it's defined, gravitational defines the gravitational potential of a point within a gravitational field is equal to the work that must be done per unit mass or per kilogram in bringing the mass from infinity to that point. So if you look at the diagram below, it's the work done to bring that mass from infinity to a certain point. So I would say really quite tricky topic. It's something you have to go back and have a look at, but hopefully this video has helped you with to develop a better understanding of gravitational potential. And if you do have any questions or comments, please do leave them in the comments section below. Thank you very much.